All right, question 6 says, let f be the vector field x cubed I plus y cubed j plus z cubed k, and D is the solid that lies between the spheres of radius 2 centered at the origin and radius 3 centered at the origin. And within the cone, z is equal to the square root of x squared plus y squared. Okay, so here's our solid pictured right up here. And our job is to find the outward flux of f across the boundary of this solid. Okay, so first thing I want to point out is that the surface of this solid consists of three pieces, right? There's this lateral piece along the cone, and then there's this bottom piece formed by the cone and the sphere of radius 2, and then this top piece formed by the cone and the sphere of radius 3. Okay, so to compute the flux integral directly would be pretty brutal because we'd have to compute three integrals. That'd be three different parameterizations, and while doable, certainly not a particularly pleasant thing to carry out. Okay, now we're going to, of course, use the divergence theorem to do this. And the divergence theorem says that we can compute this flux integral as this triple integral of the divergence of our vector field over the solid D. Okay, now the divergence is just 3 times the quantity x squared plus y squared plus z squared. Okay, so not too bad. Now, given that we're integrating over this solid that's bounded by these spheres in this cone, and looking at our integrand here, suggests we use spherical coordinates for this triple integral. And so that's what we'll go ahead and do. So we're going to let rho, which is just the radial distance from the origin, vary from 2 when we're along this inner sphere out to a value of 3 when we're on this outer sphere. Okay, and then the angle phi, okay, that's going to vary from 0 when we're along the positive z-axis out here to where we're along the cone, and that's when phi will equal pi over 4. And then theta, the polar angle, that's just going to vary from 0 to 2 pi. Okay, so we go ahead and put all of that in. Here's our bounds on rho, phi, and theta. Our integrand in um, uh, spherical coordinates, sorry, is going to be what? Well, the divergence is going to be 3 rho squared, and then we have this rho squared sine phi, and that comes from the volume element in spherical coordinates. Okay, so we can go ahead and split all of that up, and we have the integral from 0 to 2 pi of just d theta, the integral from 0 to pi over 4 of just sine phi, and then the integral from 2 to 3 of 3 rho to the 4th. All right, and kind of messy numbers there, but not difficult integrals to compute. You wind up getting 633 divided by 5 times the quantity 2 minus the square root of 2 times pi. All right, well, that does it. Thanks so much.